Imagine standing in front of a massive stone structure, its walls towering high and its arches reaching toward the heavens. These aren't just architectural marvels. They're feats of engineering that have stood the test of time for centuries. Welcome to the world of Romanesque architecture, where gravity was defied with precision and ingenuity. In the Middle Ages, engineers faced a daunting challenge: how to build structures that could support their own weight without collapsing. Enter the Romanesque arch, a design inspired by ancient Roman techniques, but refined over centuries. Unlike modern buildings, which rely on steel beams and reinforced concrete, medieval builders had only stone, mortar, and sheer determination. The secret to the Romanesque arch lies in its shape. It's not a perfect semicircle, but rather a slightly pointed oval, distributing weight evenly across its curve. This subtle modification allowed engineers to create larger spans without needing thicker walls or supports. But it wasn't just about the shape, it was also about balance. To understand how these arches worked, imagine stacking a pile of dominoes. If you push too hard on one side, the whole structure collapses. Similarly, medieval builders had to ensure that every stone in an arch was perfectly aligned and balanced. Even a slight misalignment could cause the entire structure to crumble. But how did they achieve such precision? Without advanced tools like lasers or GPS, engineers relied on simple yet effective methods. They used plumb lines, strings with weights, to ensure vertical alignment. For horizontal measurements, they employed ropes marked with knots at regular intervals. And for leveling surfaces, they used water-filled troughs, relying on the principle that water always seeks its own level. One of the most fascinating aspects of Romanesque architecture is how builders adapted to local materials. In regions rich with limestone, they constructed lighter, more delicate arches. In areas with heavy basalt or granite, they built thicker, more robust structures. This flexibility allowed Romanesque architecture to thrive across Europe, from Italy to England. But perhaps the most impressive feature of these arches is their longevity. Many Romanesque churches and cathedrals still stand today. Their massive stone walls and soaring arches a testament to the skill of medieval engineers. So next time you visit a historic building, take a moment to appreciate the invisible forces at play, the weight, the tension, and the balance that keep those arches standing tall. Picture a cathedral rising high into the sky, its walls pierced by vast stained glass windows that flood the interior with color and light. It's easy to assume modern engineering made this possible, but the truth is far more fascinating. These towering masterpieces were built in the Middle Ages using a revolutionary architectural innovation: the flying buttress. Before the flying buttress, medieval churches and cathedrals relied on thick, heavy walls to support the weight of stone roofs and vaulted ceilings. There was no room for large windows. Any opening would weaken the structure and risk collapse. But everything changed when architects began experimenting with external supports that could bear the load without blocking the walls. The flying buttress was a game changer. It worked like an invisible hand, reaching out from the upper walls of a building and transferring weight directly to massive piers outside the main structure. This allowed builders to make walls taller, thinner, and full of openings, giving birth to the awe-inspiring stained glass windows that define Gothic architecture. But how exactly did it work? Imagine holding a heavy backpack on your shoulders. Without support, your body leans forward under the pressure. Now, imagine someone behind you pushing against your back. Suddenly, you can stand straighter. That's essentially what a flying buttress does. It counteracts the outward force created by the vaulted ceilings inside, redirecting it safely to the ground through an external pier. These structures weren't just functional, they were also beautiful. Builders often adorned them with intricate carvings and statues, turning what could have been purely structural elements into works of art. Some even added decorative pinnacles on top of the piers, not only for visual appeal, but also to add extra weight and stability. Flying buttresses became a signature feature of Gothic cathedrals across Europe, from Notre Dame to Paris to Chartres and Reims. Each city developed its own variations. Some used slender arches with delicate tracery, while others favored bold, powerful forms that emphasized strength and grandeur. One of the most remarkable aspects of the flying buttress is how it transformed the way people experience sacred space. Before its invention, interiors felt dark and enclosed, lit only by small windows and flickering candlelight. With the flying buttress, sunlight poured in through enormous windows, transforming churches into radiant, heavenly realms. This wasn't just about aesthetics, it was about faith. Medieval architects understood that light symbolized divine presence. By letting the heavens shine through their buildings, they created spaces designed to lift the soul toward God. And yet, despite their elegance, flying buttresses required immense precision to build. Masons had to carefully calculate the angles and forces involved, ensuring each component worked in harmony. A single miscalculation could lead to disaster, and many early experiments ended in collapses before builders mastered the technique. So next time you see a medieval cathedral soaring above a city skyline, take a closer look at those graceful arcs stretching between walls and piers. They're not just supporting stone and glass. They're supporting centuries of human ingenuity, devotion, and artistic vision. You've seen the towering cathedrals, the thick castle walls, and the ancient bridges that still stand centuries later. But what held all those stones together? It wasn't modern cement. It was something far older, far simpler, and surprisingly powerful: lime mortar. Lime mortar was the secret ingredient in medieval construction. Unlike modern concrete, which dries quickly and creates a rigid, unyielding bond, lime mortar was soft, flexible, and breathable. And yet, it helped build some of the most enduring structures in history. So how did it work? The process began with limestone, calcium carbonate, which was heated in kilns at temperatures over 900 degrees Celsius. This intense heat drove off carbon dioxide, turning the stone into quicklime. Quicklime was dangerous. It could burn skin and even explode when exposed to water. But once mixed carefully with water, it became slaked lime, a fine white powder ready for use. Next came the mixing. Builders combined this lime paste with sand and water to create a sticky, malleable substance that could be spread between stones like glue. Sometimes they added animal hair or ash to improve flexibility and strength. The result was a material that looked simple, but had incredible properties. Unlike modern cement, lime mortar didn't harden through chemical drying. Instead, it cured slowly by reabsorbing carbon dioxide from the air, a process called carbonation. Over time, the lime mortar actually turned back into limestone, locking the structure in place with a bond that could flex without breaking. This flexibility was crucial. Stone buildings expand and contract with temperature changes, settle unevenly over time, and shift under their own weight. Rigid modern cement would crack under such stress, but lime mortar absorbed the movement, preventing catastrophic failures. That's why many medieval buildings have survived earthquakes, wars, and centuries of weathering, while newer concrete structures have crumbled. Another advantage was its breathability. Moisture is one of the biggest threats to masonry. Water gets trapped inside walls, freezes, expands, and eventually breaks the stone apart. Lime mortar allowed moisture to escape, reducing damage and keeping walls dry from within. And perhaps most impressively, lime mortar could heal itself. Tiny cracks would often fill in naturally as rainwater carried dissolved lime deeper into the wall. As this lime dried and reacted with carbon dioxide, it formed new bonds, sealing gaps before they became serious problems. In medieval times, making lime mortar was labor-intensive. Kilns had to be built by hand, fuel sources like wood or coal were expensive, and the entire process required careful handling. But despite the effort, builders across Europe relied on it for nearly every major construction project. From the great castles of England to the cathedrals of France and the fortifications of the Holy Roman Empire, lime mortar was everywhere. It was the invisible force holding up an age of stone giants. Even today, architects restoring historic buildings prefer to use lime mortar rather than modern alternatives. Because unlike concrete, it doesn't destroy the very structures it tries to repair. So next time you walk through an old church or fortress, take a moment to look at the spaces between stones. That seemingly fragile gap, it might just be the reason the building is still standing after hundreds of years. Step into any medieval village, and you'd be surrounded by wooden beams crisscrossing the walls of homes, shops, and taverns. These structures might look quaint to modern eyes, but they were built with a method that was both strong and smart: timber framing. This technique wasn't just about using wood. It was about how that wood was shaped, joined, and arranged to create buildings that could stand for centuries. Unlike stone castles or cathedrals, which took decades to build, timber-framed houses could be raised in a matter of months, making them perfect for everyday life. The secret behind timber framing lies in its skeleton. Instead of relying on thick masonry walls to hold everything up, builders used a frame made from heavy wooden beams. These frames acted like the bones of a building, supporting the roof and upper floors while leaving the spaces between open for lighter materials. Each beam was carefully cut and shaped by hand. Using tools like axes, adzes, and saws, carpenters created precise joints, mortise and tenon, scarf joints, and lap joints that locked the pieces together without a single nail. Pegs made from hardwood held these joints tight, allowing the structure to flex slightly with changes in temperature and humidity. Once the frame was complete, workers filled in the gaps with wattle and daub, a mix of woven sticks, clay, straw, and manure. This combination provided insulation, kept out wind and rain, and even helped prevent fire from spreading too quickly. Some builders used brick or plaster instead, depending on local materials and preferences. Timber framing was everywhere in medieval Europe. From London to Lübeck, from Paris to Prague, this construction method defined city skylines and village landscapes alike. In fact, many of these buildings still exist today, their crooked beams and darkened with telling stories of generations who lived inside them. But why did people love timber so much? For one, it was fast. A skilled team could raise a basic house within weeks. That speed made it ideal for growing towns where demand for housing was high. It also allowed for easy repairs. If a beam cracked or rotted, it could be replaced without tearing down the whole structure. Secondly, it was flexible. Builders could design homes to fit almost any space, adding rooms or changing layouts as needed. Multi-story buildings leaned gently inward to stay stable, and overhangs gave extra room upstairs without taking up more ground space. And third, it was beautiful. Carpenters often carved decorative patterns into beams, turning simple supports into works of art. Windows and doorways were framed with intricate joinery, showing off craftsmanship that doubled as strength. Of course, timber framing had its downsides. Wood rots, burns, and attracts pests, which is why so many surviving examples are those that were regularly maintained or later reinforced with stone or brick. Still, when properly cared for, these buildings lasted far beyond their original owners' lifetimes. Some of the oldest timber frame structures date back nearly 1,000 years. One famous example is the gingerbread house in Chester, England, built in the 14th century and still standing proudly despite centuries of weather, war, and wear. So next time you pass a half-timber building, take a closer look at those dark beams cutting across pale infill. They're not just decoration. They're the hidden skeleton that's been holding up history for centuries. If you've ever seen a medieval cottage with its dark wooden beams and pale, patchy walls, you are looking at wattle and daub, one of the most common, clever, and surprisingly sustainable building materials of the Middle Ages. Forget concrete, drywall, or even brick. For most people living in rural Europe between the 12th and 16th centuries, their homes were built from little more than sticks, mud, and straw. And yet, these walls were strong enough to last for generations. So how did it work? Wattle and daub was essentially a do-it-yourself wall system that required minimal tools and no advanced engineering. It started with the wattle, a framework of thin, flexible branches or reeds woven tightly between upright wooden stakes. This created a kind of mesh that acted as the skeleton of the wall. Once the wattling was complete, came the daub, a thick, sticky mix of clay, sand, straw, animal dung, and sometimes even human hair. Builders would slap this mixture onto both sides of the wattle, pressing it deep into the weave so it stuck firmly. After drying in the sun, the result was a solid, weatherproof wall that could insulate against cold winters and hot summers. One of the biggest advantages of wattle and daub was its availability. Unlike stone or timber framing, which required skilled labor and heavy tools, anyone with basic tools and access to local materials could build with wattle and daub. That's why it became the go-to method for peasant homes, barns, workshops, and even parts of churches. Another benefit? It was eco-friendly, long before sustainability became a buzzword. All the ingredients were natural, biodegradable, and often sourced from nearby fields and forests. There was no industrial manufacturing involved, no carbon-heavy production, just earth, plants, and muscle power. And despite its humble origins, wattle and daub had real strength. When properly maintained, these walls could support upper floors, resist wind, and even slow the spread of fire, especially when coated with lime wash or plaster. But it wasn't without its challenges. The biggest issue was durability. Without regular maintenance, wattle and daub walls could crack, erode, or collapse under heavy rain or flooding. Rodents loved burrowing into them. Termites and other pests found them cozy and easy to chew through. So homeowners had to keep an eye on their walls and patch them up regularly, kind of like repainting a house today. Still, for ordinary people who couldn't afford stone or timber-framed houses, wattle and daub was the perfect solution. It was fast to build, cheap to repair, and incredibly effective for its time. Some surviving examples still stand today, centuries later. In places like England, Germany, and France, you can walk into homes built in the 14th or 15th century and still see the original wattle and daub hidden beneath newer plaster or paint. In fact, some modern builders are even bringing back wattle and daub techniques for eco-housing projects. With rising concerns about climate change and construction waste, ancient methods like this offer a low-impact, high-efficiency alternative to synthetic materials. So next time you see a crooked old cottage leaning slightly sideways, remember, behind those cracked walls is a history of ingenuity, resourcefulness, and a surprisingly green approach to building. If you've ever walked through a medieval church or castle and noticed an arch that looked like an elegant S shape, rising steeply before curving inward at the top, you were looking at an ogee arch. Unlike the simple semicircular Romanesque arch or the pointed Gothic arch, the ogee was a masterpiece of form and function. It wasn't just decorative, though it certainly added visual flair. It was also a structural marvel that allowed builders to push the limits of height, light, and space in ways never seen before. The ogee arch is defined by its double curve, a lower section that rises upward in a concave shape, followed by an upper section that curves outward like a bell. This unique profile gave buildings a sense of movement and elegance, making them feel less rigid and more dynamic than earlier architectural styles. But why did medieval builders start using this design? As the Gothic period progressed, architects wanted to build taller, lighter structures with larger windows and more intricate details. Traditional pointed arches helped distribute weight efficiently, but they still had limitations when it came to ornamental design. Enter the ogee arch. It became especially popular in late Gothic architecture across England and France, where it was used not only for doorways and windows, but also for vaulted ceilings, arcades, and even decorative tracery within stained glass. One of the most striking uses of the ogee arch was in the design of window heads. Builders began shaping the tops of windows into flowing, undulating forms that mimicked natural patterns like waves or vines. These designs weren't just artistic flourishes. They also helped support heavier stonework above while allowing for thinner walls below. Another advantage of the ogee arch was its ability to blend seamlessly with other Gothic elements like crockets, finials, and pinnacles. Together, these features created a sense of verticality and grandeur that made churches and cathedrals look like they were reaching toward the heavens. Perhaps one of the best examples of the ogee's beauty can be found in English perpendicular Gothic architecture, particularly in places like Gloucester Cathedral and Westminster Abbey. Here, ogee arches frame choir stalls, tomb niches, and cloister walkways, adding a sense of rhythm and refinement to the interiors. Beyond aesthetics, the ogee arch also had practical benefits. Its curved shape allowed for better distribution of pressure from above, reducing stress on keystones and supporting structures. This meant that builders could create more complex and elaborate designs without compromising stability. In domestic architecture, the ogee arch was often used in fireplaces, doorways, and timber-framed houses. It became a symbol of sophistication, a way for wealthier homeowners to show off their taste and status through subtle yet unmistakable design choices. Even today, the ogee arch continues to influence modern architecture and interior design. You'll find echoes of it in crown moldings, arched doorways, and decorative windows in homes and public buildings around the world. So next time you see that elegant S-shaped curve in a medieval structure, remember, it's more than just a pretty shape. It's a testament to centuries of innovation, craftsmanship, and the enduring desire to make buildings not only strong, but beautiful. You're standing beneath a medieval roof, rain drumming steadily above you. Water trickles down the sloped tiles, following paths carved by centuries of design and necessity. There's no leak, no damp ceiling or dripping eaves. Just quiet, dry shelter. This wasn't luck. It was engineering. In a world without modern plumbing, insulation, or synthetic materials, medieval builders faced a constant battle against water. Rain soaked through poorly made thatch, wooden shingles rotted under constant exposure, and even stone roofs could crack under temperature changes. But there was one solution that changed everything: the tiled roof. Tiles weren't just about durability, they were about precision. Each curved or flat piece was carefully placed in overlapping rows, creating a barrier that guided water away from the building rather than letting it soak in. This system, known as a weathering layer, ensured that water ran off smoothly instead of seeping into the walls or rafters. Unlike thatch, which needed frequent replacement, or wood shakes, which warped and split, clay or slate tiles lasted for decades, sometimes centuries. Some medieval tiled roofs still exist today, silently proving their effectiveness. So how did this innovation begin? The use of roof tiles dates back to ancient Rome, where large villas and public buildings featured them to keep interiors dry. When the Roman Empire fell, much of this knowledge was lost in Western Europe, but not forever. By the 12th century, as towns grew and trade expanded, kilns capable of firing durable ceramic tiles became more common. Builders rediscovered the advantages of tiling, especially in areas with heavy rainfall like England, Germany, and the Low Countries. There were two main types of tile used. Plain tiles, also called flat tiles, were rectangular or square-shaped and laid in tight rows. Pan tiles, named after the Italian pan tile, were S-shaped and interlocked, allowing water to flow seamlessly from one to the next. Both styles relied on a simple but brilliant principle: gravity and overlap. Tiles were fixed to wooden battens at an angle that encouraged water to run off quickly. Each row sat slightly higher than the one below, ensuring that water never had a direct path inside. But tiled roofs weren't just about keeping dry. They offered other benefits too. They were fire-resistant, a major advantage in densely packed medieval towns where open flames and wooden structures were a dangerous mix. They provided better insulation, helping homes stay cooler in summer and warmer in winter. And unlike thatch, they didn't attract rats or insects, making them safer and more hygienic. Of course, there were downsides. Tiled roofs were heavier than alternatives like thatch or wood, so buildings needed stronger timber frames and sturdier foundations. Production was labor-intensive, and transport costs could be high if tiles weren't made locally. Still, for wealthier homeowners, monasteries, and civic buildings, the investment paid off. A tiled roof meant fewer repairs, less risk of fire, and long-term protection from the elements. Some of the oldest surviving tiled roofs in Europe date back over 700 years. In places like Exeter Cathedral and Bruges historic townhouses, these roofs remain functional, silent witnesses to storms, wars, and centuries of history. So next time you see a medieval building with its original roof intact, take a closer look at those weathered tiles. Beneath their aged surface lies a story of ingenuity, resilience, and the quiet genius of medieval builders who refused to let the rain win. Imagine standing near a roaring fire, heat radiating from a massive earthen chamber as glowing embers light up the night. This is no ordinary bonfire. It's a medieval brick kiln, and inside it, history is being baked into stone. Bricks might not seem like a big deal today. We see them in walls, pavements, and facades all the time. But in the Middle Ages, bricks were revolutionary, especially in regions where good building stone was scarce or difficult to quarry. Unlike sun-dried mud bricks used for thousands of years in warmer climates, medieval builders discovered that by firing clay in specially designed kilns, they could create strong, weather-resistant bricks that could last for centuries. And once they figured out how to mass-produce them, entire cities began to change. So how did they do it? It started with the right kind of clay, not too sandy, not too silty. The best clay had just the right amount of plasticity, meaning it could be shaped and dried without cracking. Workers dug it from local pits, often near rivers, then mixed it with water and left it to age. Some even trampled it barefoot, or let animals do the job, to remove air bubbles and ensure an even texture. Once ready, the clay was molded into rectangular shapes by hand. Wooden molds, sometimes lined with sand or straw to prevent sticking, helped workers produce uniform bricks. These are then left to dry for several weeks before firing. The real magic happened in the brick kiln itself. Unlike modern industrial kilns with precise temperature controls, medieval kilns were simple but effective. They were usually dome-shaped or rectangular structures made from already fired bricks or built directly into the ground. There were two main types: intermittent kilns, which were loaded with green, unfired bricks, sealed shut, and fired until the bricks turned hard and durable. Continuous kilns, like the Hoffman kiln, developed later but inspired by earlier designs, allowed bricks to be added and removed while the fire kept burning. Fuel varied depending on location. Wood, charcoal, peat, or even animal dung was used when nothing else was available. Temperatures could reach over 1,000 degrees Celsius, turning soft clay into rock-hard bricks capable of withstanding wind, rain, and even fire. But this process wasn't easy. It required skill, patience, and a deep understanding of heat and airflow. Too much heat, and bricks could melt or warp. Too little, and they would remain soft and fragile. Despite the challenges, brickmaking became a vital trade across Europe. In places like the Netherlands, Germany, and parts of England, brick replaced stone as the preferred material for everything from churches and town halls to houses and bridges. One of the most famous examples of medieval brick architecture is the Kerk in the Netherlands, a church built almost entirely from brick, including its intricate vaulted ceilings. In northern Germany, entire towns were constructed using red brick Gothic techniques, creating some of the most iconic medieval skylines in Europe. Brick also gave builders more freedom. It could be cut, carved, and laid in complex patterns that weren't possible with rough-hewn stone. This led to decorative elements like arched doorways, ornamental banding, and even sculpted friezes, all made possible by the versatility of fired clay. And unlike timber, which rotted or burned easily, or wattle and daub, which needed constant repair, brick buildings lasted for generations. Many still stand today, silent witnesses to wars, floods, and centuries of history. So next time you walk past a wall made of old red bricks, take a moment to appreciate the craftsmanship behind each one. Those bricks didn't just shape buildings, they helped shape the future of construction. Step inside a medieval cathedral or castle and look up. What you see isn't just a ceiling. It's a masterpiece of engineering and artistry that has held up stone and sky for centuries. Vaulted ceilings were more than just decorative marvels. They were the solution to one of the biggest architectural challenges of the Middle Ages: how to support massive stone roofs without crushing everything underneath. In the early Romanesque period, builders used simple barrel vaults, essentially continuous arches stretched across a space like a tunnel. These worked well enough, but they had a serious flaw. They pushed outward with incredible force, threatening to buckle walls if not properly supported. To solve this problem, medieval architects evolved their designs into something far more sophisticated: the ribbed vault. This innovation became a defining feature of Gothic architecture. Instead of relying on solid masonry, builders created a framework of intersecting stone ribs that carried weight down to piers or columns at key points. This allowed for taller buildings, thinner walls, and most importantly, more light. Imagine walking through a vast church where sunlight streams in through towering stained glass windows, illuminating the stone above you. Without ribbed vaulting, none of that would have been possible. But how exactly did these ceilings work? Each vault was made from carefully cut and shaped stones called voussoirs, which locked together around a central keystone. Unlike modern concrete, which is poured into molds, each piece of a medieval vault had to be carved precisely so that it fit perfectly under pressure. The process began with wooden scaffolding called centering, built in the exact shape of the intended vault. Masons then placed each stone by hand, working from the bottom up until they reached the top, where the keystone completed the structure. Once the keystone was set, the centering could be removed, leaving behind a self-supporting ceiling that could hold its own weight and more. One of the most remarkable things about these vaults was their ability to distribute stress efficiently. Instead of forcing all the weight straight down, ribbed vaults channeled forces diagonally toward the corners of the room, reducing lateral pressure on the walls. This breakthrough allowed architects to build structures that soared higher than ever before, cathedrals with ceilings that seemed to vanish into the heavens. Some of the most famous examples include Notre Dame de Paris, where intricate ribbed vaults stretch over the nave and choir; Canterbury Cathedral, where early experiments in vaulting led to increasingly ambitious designs; Durham Cathedral, home to some of the earliest surviving ribbed vaults in Europe, dating back to the early 12th century. Beyond their structural advantages, vaulted ceilings also had a powerful visual effect. The interplay of light and shadow along the curved surfaces created a sense of movement and depth. The patterns formed by the ribs guided the eye upward, reinforcing the spiritual atmosphere of religious spaces. Even secular buildings adopted the technique. Great halls and castles featured simpler versions of vaulting, sometimes even painted or decorated with heraldic symbols. These ceilings weren't just beautiful. They were statements of power and prestige. Of course, building them wasn't easy. It required years of training, precision-cut stonework, and an understanding of physics that medieval builders developed through trial, error, and generations of experience. Despite their complexity, many of these vaulted ceilings still stand today, silent testaments to the skill and ambition of those who built them. So next time you find yourself beneath a vaulted ceiling, take a moment to appreciate what you're seeing. Those graceful curves aren't just there for show. They're the result of centuries of ingenuity, strength, and the desire to reach beyond what seemed possible. Stand in front of a medieval castle wall or cathedral and run your hand across the stone. Smooth, cold, and impossibly tight-fitting, as if the blocks were poured into place rather than carved by hand. But that's exactly what happened. Each stone was shaped with precision, measured without modern tools, and laid without mortar strong enough to hold them forever. And yet these walls still stand. Medieval masonry wasn't just about stacking rocks. It was an art form, a science, and a testament to human skill. These builders had no cranes, no power tools, and no concrete glue like we do today. They worked with chisels, hammers, and sheer muscle. And somehow, they made it look effortless. So how did they do it? It started with the stone itself. Builders chose limestone, sandstone, or granite based on local availability and durability. Limestone was popular because it could be cut easily when fresh and hardened over time. Granite, though tougher to shape, lasted for centuries without wear. Once quarried, raw stone was delivered to the construction site, often by oxen-drawn carts over rough dirt roads. There, skilled masons took over. These weren't just laborers. They were master craftsmen who spent years learning the trade. Each block was carefully shaped using a few simple tools. Mallets and chisels for carving and smoothing. Scabbling hammers for rough shaping. Set squares and plumb lines to ensure perfect angles. Templates and wooden gauges to replicate complex shapes. Every stone was unique, especially in vaulted ceilings and arches, where each piece had to fit precisely to lock under pressure. A single mistake could mean redoing the entire section. One of the most impressive techniques used by medieval masons was dressing the stone. This involved smoothing the outer surface to create a finished look while leaving the edges slightly raised, a technique known as belection molding. This not only improved aesthetics, but also helped shed water away from the joints, preventing erosion. But perhaps the most fascinating method was dry fitting. Before final placement, stones were test-assembled without mortar to check alignment. Only once everything fit perfectly was the stone set in lime mortar and locked into place. This attention to detail explains why so many medieval structures have survived wars, earthquakes, and centuries of weathering. Another secret to their success? Jointing. Unlike modern buildings that rely on thick layers of cement, medieval masons used thin, precise mortar lines. Too much mortar could crack under pressure. Too little left gaps that weakened the structure. Finding that balance required experience passed down through generations. Some masons even signed their work, not with names, but with small marks carved into hidden parts of the stone. These mason marks acted like signatures, allowing master builders to track quality and assign credit or blame for errors. In large projects like cathedrals, teams of masons worked side by side, each responsible for a section of the building. Some specialized in arches, others in columns, and some focused solely on decorative carvings like gargoyles, tracery, and biblical scenes. Even the simplest buildings benefited from this expertise. Village churches, bridges, and town walls all bore signs of careful planning and execution. And in castles, where strength meant survival, masonry reached its peak, with massive curtain walls, round towers resistant to siege weapons, and inner keeps built to withstand months of attack. Despite the lack of modern technology, medieval masons achieved something remarkable. They built monuments that outlived their creators, structures that still speak to us today, whispering secrets of the hands that shaped them. So next time you walk past a medieval wall or step inside a centuries-old church, take a closer look at those stones. They didn't just fall into place. They were placed there one by one, with incredible care, skill, and patience. Now, if you enjoyed this video and want to see more content like this, don't forget to hit that like button, subscribe, and turn on notifications so you never miss another episode of history's darkest, weirdest, and most fascinating moments. Because trust me, the past has a lot more to tell.